Hi there, welcome back to the channel, and in today's video we will be discussing how to calculate equivalent inductances in series and parallel connections. And just to start the video off, let's start by discussing these formulas I'm showing to you right now, the series formula and the parallel formula. So inductors, we measure inductors in inductance, and that unit of inductance is in henries. So if we have this inductor Lx would have a value of, in this example, 1 millihenry. And now let's consider two inductors to build up from that. So here we have an inductor, L1. Here we have an inductor, L2. L1 is equal to L2 in this case. So therefore, they both have values of 50 millihenries in this example. So let's apply those formulas to see what happens to the overall inductance. So let's first consider series connection. If they are both connected in series, again applying this formula, L2 equals L1 plus L2, we have an overall inductance then, in the case of this example, of 100 millihenries, because it's a simple case of addition for a series connection. Now for a parallel connection, we have to use the parallel formula in this form. So we could say that LT is equal to 1 over L1 plus 1 over L2, all of that in a bracket, raised to the power of minus 1. So, in this case, if we insert those values, we actually get a value of 25 millihenry. So, the trend here is that if your inductors are connected in series, you will have a larger inductance. If your inductors are connected in parallel, you will have a smaller inductance. That's a general trend that you should be aware of, and it can help you understand if you have the right answer or not. So now, this is a lot of what you need to know about how to calculate series and parallel inductances. Let's apply these to some other problems so you can have a go for yourself. Okay, for this first problem, what I want you to do is to ignore the voltage source and just focus on calculating the total inductance of this circuit. Take your time if you need to and pause the video to work on the solution. Okay, the first step here is to focus on L2 and L3 because they're in parallel. So we have 100 microhenries in parallel with 50 microhenries. So what we need to do here is apply the parallel formula of 1 over 100 times 10 to the minus 6 plus 1 over 50 times 10 to the minus 6. Raise all that to the power of minus 1, and we get an answer of 33.33 recurring microhenry. So now that we've calculated that equivalent half of the circuit, they're now in series with L1. That equivalent inductance for L2 and L3 is now in series with L1. So now it's a case of 50 microhenry plus 33.33 recurring microhenry, which will give us an answer of 83.33 recurring microhenry. That is the total inductance of the circuit. Okay, same style of problem once again, but just a bit more complex. Again, ignore Vs, the voltage source, and just focus on calculating LT, the total inductance of this circuit. Take your time if you need to, and pause the video to work on the solution. Okay, let's start by simplifying the right hand side. So L4 and L5 are of identical value, and they are 500 microhenries. And that is equal to 1 millihenry. And that's in series with L3. So L3 and L4 and L5 is equal to 2 millihenry. That's now in parallel with L2, the 12 millihenry. So moving to the bottom left, 1 over 2 millihenry plus 1 over 12 millihenry raise that all to the power of minus 1, and our answer is 1.71 millihenry. And that's now in series with L1, 10 millihenry. So our final answer for the total inductance is 11.71 millihenry. Okay, that's all for today's video. Thank you very much for watching, and I hope you learned something new about series and parallel connections of inductors and how to calculate their equivalent inductances. In next week's video, we will be considering the transient response of an inductor. Thank you once again for watching.